Sup everyone, I'm Kevin, and today we'll talk about code complexity. That's a very important tool to distinguish between two pieces of code, two algorithms, and picking the one that fits your needs the best. I'll also give some tips regarding coding interviews because this is a very important topic when we think about code interviews in general. Of course, more common on big techs, but I've been asked before, even for smaller companies, about code complexity. I prepared some slides. The first thing I want to mention is that when we talk about code complexity, we might be worrying about speed or about memory, or usually both. But it's important that you know your constraints because if during a job interview someone asks you, do that, I want a solution that does that. If you don't ask about the constraints, it might seem like you don't know how to pick the correct solution. You are just building it and that's it. But the context might change what you're building. And we'll have clear examples through this video. But yeah, how picking the wrong algorithm affects performance. What I actually want to bring up here is that sometimes we might be worried like, hey, until here, this algorithm here, this function is performing a little worse. It's using more time than this one. So maybe we should use this one. But when we are worrying about algorithms, about code complexity, we are usually worried about big data sets. Because otherwise, let's say you have an array of 3 elements. Does it really matter that much the algorithm you're using, for example, to sort them? I don't think so. Yeah, what will really affect your code is that. And about the big O notation, it's the notation we are using here, and it's the most common one. The big O is a notation that is used to represent how complex a piece of code is. And it worries about the worst case scenario. Let's check an example. Right here, we have a function called findX. It iterates through an array and will check for each item of the array if it matches the value of x. If it does, we'll just return. Here's one question. How many times will we run this line? Your answer might be it depends, because if the first element of the array already matches x, then we are returning and escaping the function. That's true, but once again, we are talking about big O here, worst case scenario. So we'll consider that it will be the last item of the array, or any item, if any. Maybe it doesn't match any item, and we'll log x not found. So it might run n, being n the length of the list, times plus 1, because last one is just to the false check. Like I is less than 10, it's not. So we won't enter anymore, but we run here once again. So n plus 1 on this first line. Oh, it's even more because we have many operations here. We are declaring a variable, we are assigning a value, we are doing this comparison, we are increment. I know, but it shouldn't matter. I shouldn't even matter about this one. We got there. So if we'll run it for each iteration, so n times, and this console log here will just run once, because after that we are returning, escaping the function. So the complexity of this piece of code will be the sum of operations, though we're not counting each operation. So it will be n plus 1 plus n plus 1, or 2n plus 2. When we represent that with the big O of 2n plus 2, it becomes just O of n, because the constants don't matter, and the multiplying factor here also doesn't matter. And why doesn't it matter? Because getting back to charts, like now instead of just x, I'm multiplying x by 50. I could be multiplying by 1,000 and something 200. But even though it seems like this one is way worse than this one, when you actually go through large sets of data, this one will eventually reach the green line and we'll go over it. So what really matters here is the power, the number that x is being, or n or whatever, is being powered to. So yeah, for big O notation, we shouldn't care about this two and this two, just n. Here we have a complexity chart. It's showing some of the most common values we use to represent the code complexity. And it's trying to label them as excellent, good, fair, bad, horrible. But I want you to not care that much about those labels because sometimes, many times, maybe the best solution for your case is actually something that is O n squared. It isn't possible to do everything with O of 1, for example. But if you see something like n factorial, then I would say you should worry a little bit just because there might be better options. But it's not uncommon at all to write scripts that they need to be n squared. About O of n, which is the one we just saw with the for loop, I think the best way to represent it is when we have to iterate through an array, even if we have to run more than once. But what about n squared? For me, the best way to represent it is with matrices. I'm using a matrix here, defining it, and I still have a function called findx, but this time I have to iterate through 2 dimensions. So for example, while I is 0, which means first row, I have to go with through each item. Then I1, each item. In the end, the amount of operations we are doing really increases according to the size of the data, of the input. So for this one would be O of m times n, being m and n dimensions. Or simplifying, of n squared is quadratic. If we had a third for loop here nested, we would have n to the power of 3 here, and there you go. But if the for loops were all on the top level of the function, so sibling for loops, then it would be 1n, 2n, 3n, the amount of times it would iterate. We would not consider this multiplying factor. We would just consider O of n, because that's what really matters when we are picking between 2 algorithms. O of 1 is when we don't have, for example, to iterate through an array, because the size of the input shouldn't matter to scale the code on big O notation. So for example, I brought some more complex examples here. Not complex, but for example, we have a function here called get third fruit. And first thing you should know, to get an element from an array by the index, it's O of 1. So it doesn't matter if the array has 1 element or 1,000 elements or 1,000,000,000 elements. It should be O of 1. It doesn't scale together. So this is a function O of 1. And the same is true for hash tables or objects in JavaScript. For accessing properties, even if person had 1,000,000,000,000 properties, that's just O of 1. So what about O of log of n? Or simplifying a little, what the hell is log of n? Because we don't use it daily. We don't go shopping and we use log of n to figure stuff out. The way I see, the way I learned as a kid is that when you have, for example, x to the power of y equals z, if we swap those 2 values, then it's still x here, but we swap this one. It's the same as writing log of z to the base x is equals to y. Giving a clear example here, it's like saying that log of 8 base 2 is 3. So if we swap those values, 2 to the power of 3 is 8. 2 times 2 times 2. And also important to mention, when you are working with math, if you just see log written without the base, it means that the base is 10. But if you are working with programmer, with computer science, if you just see log, it means the base is 2. So yeah, we are working here with log base 2 when I say log of n. Example of how it applies to algorithms, to code complexity. Let's say we have an array that we know for a fact it's ordered, but we don't know where exactly is each element or what it is. Like a dictionary, if you compare to real life. So if you have a dictionary, you can find a word going page by page until you get there. But that's not very effective. A better method would be to just split the dictionary in half and checking, is the word I'm looking for on the back or forward? And then open the other half and half until you get to the word you want. That would be more effective. And that's what we are doing here. That's called binary search. The first example, going page by page, or if I want to find 10, is this 10, is this 10, is this 10, is this 10? That would be linear search. How binary search works is, we want to find 10, we will split this array in half, and I'll always check in the example for the value on the left. I could check for the one on the right too, but just to pick one, 15. Is 15 greater than 10? Yes. So I'm gonna divide on the left side. I don't consider this one anymore. So getting the new half is 7. greater than 10? No, it's less. Then I'm gonna look to divide this part into 11 greater than 10. So I'll divide this one into 10 is 10. So we found our value. Notice that was the worst case scenario. The best case scenario would be if I was looking for 15. So as soon as I split, oh, 15. That's it. But even though it was the worst case scenario, we just had to do 4 operations, dividing once, twice, the third time, and the last one, the fourth. If we were to check the worst case scenario to do a linear search here, which would be to find the 31, we would have to go through all elements. It would be a O of n. In this case, 16 iterations. But when we are always dividing by 2, the question should make for the worst case scenario is how many times can I divide it by 2? Because if you divide by 2, let's say in this case 4 times, and then you get to one element, it can only be this element or none. That's why the code complexity for a binary search is log of n, because asking how many times you can divide something by 2 is the same thing of asking what's the log of 16 base 2. Remember swapping the value, log 6 and the x here, if we swap, 2 to the power of what of x is 16. If you didn't understand that, please try again, go over this part of the video, because that's the most visual I can be. And yeah, O log of n, sorry, let me put it here. And sometimes you'll also see n times log of n. If you see that, what it means, maybe we have 2 arrays, and one of them will be this one, the one we are trying to find the values on, and the other one will be the values to be found. We have 2 big inputs, and for each one of them, we'll do a binary search. So n times log of n, n, log of n, log of n. And that's the O n log of n. Make sense? Hopefully, if we check, once again, the big O complexity chart, we just went through the O log of n and the n O of n log of n. We started with the O of n, then O n squared, and we also did the O of 1. We just have those 2 remaining, but they are too complex, so I won't spend that much time on them. For this one, Fibonacci. If you don't know what Fibonacci is, it's a sequence of number that it starts with 1 and 1, and the next value is always the sum of the previous 2 values. For example, 1, 1, the next value should be 2. 2, 1, next value 3. 3, 2, next value 5. And there you go. 8. Anyways, that's the way of building a Fibonacci function. And what I wanted to return to the O of 2 to the power of n is that for each number, for the number that we pass here, for each one of them, we're going to call the function twice. So that's why it's 2 to the power of n. I hope that's clear. According to the chart, that's not the most performatic one. And the most stupid one that I couldn't think of a better example, sorry for that, is the factorial. The factorial is even hard to explain. Not the factorial, sorry. Yeah, the factorial. It's the n factorial. So I built a function that calculates the factorial of a number. Factorial is, for example, factorial of 4. 4 times 3 times 2 times 1, which would be 24. So that's what my function calculates, and it's of the complexity of O of n factorial. And usually I wouldn't build a factorial this way, but I did it in the dumbest way I could just to have an example of this. I don't want it to hurt your brain trying to understand this, but what I wanted to understand is when I call this function, it will iterate and then call factorial here, which will iterate again. And it's like for every element we have a new loop. So that's the factorial one. It's hard, don't try to understand this function if you don't feel like it. It's not important. I just wanted to know that it's complex and it's not performatic in general. Alright, so small challenge. If you want, you can stop the video here, just pause it for a second and try to guess what's the code complexity here. What is this function? Check the first repeated value. So for this one, like we'll get, for example, the I0, and inside the J, we'll be comparing, hey, is this 0, is this 0, is this 0? And we would be doing that to the end, and then second number, check for equality, this one, equality. What is the complexity of this code? I hope that just by looking at this, you can already tell it's a n squared, n to the power of 2, because we have nested for loops. But I didn't like this implementation, and I wanted to do something that would be faster. So I created the second version, same function, but this one I have a constant map here, an object, and for now forget this if. I keep saving on the map the key being the element, like 0, and assigning true to it. So in the end, I'll be creating an object shaped like this. And the question this if is asking is, have I seen this before? So the idea is, I'll go through each element and save it here. Remember, to access the key of an object or an array element by the index is complexity O of 1. So we don't even consider, we have a for here, it's already O of n at least. So for each one, I'll be saving until I check, oh, I've seen this before. It returns true. Then I just return the number. My question here is, what's the best implementation between those two? If you're answering one of the or the other, the actual answer that I wanted depends on the context. Because once again, remember what I was mentioning at first? Ask the interviewer for the constraints. So if the interviewer says, for example, the list might be huge, it might be a very big list, and you don't know if your computer can handle all the memory, then this approach is not good because, attention now, the code complexity, memory-wise, is O of n. Get it? That's the important part, because we use the same method to calculate the memory complexity. What it means is, for each element, I'll save an element here again. So that's where I wanted to get, because to calculate complexity regarding memory, you'll use the same knowledge we just used to calculate the speed complexity in general. Yeah, in this case, once again, you ask the constraints to the interviewer, and if he said, oh, we have a memory constraint, the list is too big, you wouldn't go with that approach, but with this one. And it wouldn't be unrealistic for the interviewer to just say, hey, we don't have constraints right now, you go with this one, and then he says, yeah, but now let's imagine you have a huge list and you can start. How would you do? Then you would go with this other approach here and explain. Yeah, for this one, so since I can start the values, I'm gonna have to use n squared complexity, and yeah, it will decrease a little bit the performance, but now it's usable for our case. And that's it. I really hope you liked this video, and mainly that you understood the log of n, because I think it's one of the scariest ones, because people don't usually understand log in general. So yeah, please leave comments here if you have any questions or comments in general. Like the video, subscribe to the channel, and I'll see you on the next one.